In this lesson, you will learn how to use factor trees to write a number as a product of prime numbers. Now, before we get into the process of using factoring trees, we first need to remember what does the word factor mean, and then what does the word prime mean. So the first word, factor, remember, are numbers that are being multiplied together. So for example, if you're multiplying 4 times 5 and that product is equal to 20, 4 and 5 are called the factors. So these two numbers are factors, and then 20 would be called the product. So factors are numbers that are multiplied together. And then the next term is going to be prime numbers. But to understand prime numbers, we also need to understand what is a composite number. So a composite number, remember, has more than two factors. So for example, if you had the number 20, all right, 20 would be composite because if you think through what multiplies to get 20, we would have 1 times 20, but we also have 2 times 10, or we have 4 times 5. So our factors would be 1, 2, 4, 5, 10, and 20. So there's 6 factors here. So because it has more than 2 factors, this would be composite. Now a prime number has exactly 2 factors. So for example, if you had the number 11, 11 is prime because the only way to get 11 would be 1 times 11. So the only factors of 11 would be 1 and 11. So just 2 factors. So anything like that is going to be a prime number. Now what we're trying to do in this lesson is we're trying to take a composite number, something like 20, and then break it down as a product of prime numbers. So what does that mean and what does that look like? Well, that process is called prime factorization. We are taking a number and writing it as a product of prime numbers. So we're taking factors, prime factors, and multiplying them together to get to 20, or to get to some number. So for example 1, here we have 20 as our number. This number is composite, right? We just verified that in the last slide. Well, our goal is to break this down so that we have a bunch of prime numbers multiplied together to equal 20. So there's different ways you can do this. There's not one set way, but if we use a factoring tree, okay, factoring tree is going to be like this, where we have 2 lines coming down, and we think through, okay, what can we multiply together to get to 20? Well, different numbers would multiply to get 20. It could be 2 times 10, it could be 4 times 5. We're going to choose 4 times 5. So 4 times 5 equals 20, right? That's what we have here, 4 times 5. Now, 4 is composite, right? Because 4 would be 1 times 4, but it also could be 2 times 2. So 4 is composite. We can break this composite number down further. So 4 we can break down as a product of 2 times 2, right? 4 is 2 times 2. All right, 5, this number right here, that is going to be prime. So this number is good. Like, we cannot break it down any further. So we could just kind of carry it down to the next line because it's already broken down as far as it can go. So what we can do is now we have 2 times 2 times 5. And would you agree? Would that equal 20? Well, yeah, that would, right? 2 times 2 times 5 does equal 20. So now we have to look at these numbers, the 2, 2, and 5, and see, is there any composite number that we can break down further, just like we broke the 4 down into 2 times 2. Well, this whole entire row is now prime. All right, the 2 cannot break down any further, the 5 cannot break down any further. So what we've done is we've broken down 20 as a product of 2 times 2 times 5. So this answer right here of 2 times 2 times 5 is the prime factorization of the number 20. We've broken it down as a product of prime numbers, and that was our objective. And this right here, this is called a factor tree because it looks kind of like a tree, right? So if you draw a tree out, it's going to look, something kind of like this, right? That's a beautiful drawing of a tree, right? So it looks kind of like that. See how it's small on the top, it gets bigger on the bottom. It's kind of like a tree. So that's why it's called a factor tree. So that is the process. And what we have now is going to be just several more examples that you can practice with. So we're going to walk you through a couple, and then we'll give you a couple to practice on your own. If you're already understanding, see if you can do as many of these as you can by yourself. So like pause the video if you need to, and then see if you can do it on your own. And then you can unpause when you're ready and see if you got the correct answer. So our next number we're gonna do is 36. So our objective is to break this down as a product of prime numbers. What is the prime factorization of 36? Well, to do this, we can create a factor tree, just like we did over here for 20. And we can break down 36 as a product of different numbers. Different ways you could do this. You could do 2 times 18. You could do 3 times 12. You could do 6 times 6. You could do 4 times 9. So there's not one set way to do this, but your end answer will always be the same. So we're going to choose to break this down as a product of 6 times 6. Right? That is a true statement. 36 does equal 6 times 6. Now, the 6's, is that prime or composite? Well, that's composite, right? Because 6 can be broken down further. All right, it can be broken down as a product of 2 times 3. So we can break apart the first 6 as 2 times 3, and then the other 6 over here can also break down as a product of 2 times 3. So now we have this new row of numbers right here. So now we have 2's and 3's. And the question is, are any of those composite? Can we break down any of those numbers further? Well, the answer is no. These are all going to be prime. Those cannot be taken any further. So 36, we can think of it as 2 times 3 times 2 times 3. And we see that typed up right here. Now, it's typically best practice to put the numbers in order from least to greatest. So if you put them in order, we would have 2 times 2 times 3 times 3. So this is the better way of writing your answer. So your prime factorization is right here, the 2 times 2 times 3 times 3. That is the prime factorization of the number 36. All right, so that was example 2. Let's try another example. Here we have 200. So how can we write this as a product of prime numbers? So different ways you can do this. So one way is realize that 200 you can divide by 10, right? If we do 10 times 20, that gives you 200. So you can do it this way. You could do 2 times 100 if you find that simpler. Either way, we're going to get the same final answer. And you can check to see if that's true. You can check that. Try a different method with different numbers and see if you get the same end result. And you will find that it's going to be the same answer. But we're doing it this way here. We have 20 times 10. And now looking at this row of numbers, the 20 and the 10, we need to determine, are those numbers prime or composite? Well, they're both composite, right? Those can both be broken down further. 20, we can break down different ways. One way is we can break it down as 4 times 5. And then the 10 is also composite. We can break that down further as 2 times 5. All right, so what we have now is 4 times 5 times 2 times 5. And if you multiply those together, at this point, it would still equal 200. So now the question is, with this row of numbers, are those numbers prime or composite? Well, the 5 and the 2, those are going to be prime. Those cannot be taken any further. But the 4 out here, that number is composite. So this 4, we're going to take and break it down further. 4 can break down as a product of 2 times 2. And then these other numbers here, the 5, 2, and 5, we need to carry down to this next row. So don't forget about them. 5, 2, and 5. So bring those down. And now what we have is 200 equals 2 times 2 times 5 times another 2 times another 5. And now we look at those numbers and see, are those prime or composite? Well, all of those are prime now. Those cannot be taken down any further. So we've broken it down as far as we can. These are all prime numbers. So we can write this now as a product of those prime numbers, where we have 2 times 2 times 5 times 2 times 5. And again, typically it's best practice to write these in order from least to greatest. So put the 2's together and then the 5's together. So we have 3 2's multiplied and then 2 5's multiplied together. So we have 2 times 2 times 2 times 5 times 5. And this would be the prime factorization of the number 200. So that is the process of prime factorization. We've given you 3 examples. And if you're doing well with understanding, you could jump ahead past this next slide here, because what we're going to do is we're going to give you 3 more to practice with if you need it. So if you don't need it, you can skip ahead. If you want the practice, here are a couple more examples. So we have 3 examples on this slide. First one is, what is the prime factorization of 12? So try this one, see how you do. And 12, different ways we can do this. One way is we can think of 12 as, let's do 4 times 3. All right, so that can break down. Now 3 is prime. That cannot be taken further. 4 is composite. We can take that further. 4 we can think of as 2 times 2. And then 3 we can bring down to the next line. Now 2 is prime and 3 is also prime. That is as far as we can go. So put that all together. We have 2 times 2 times 3, and that is the prime factorization of 12. Because if you multiply together, 2 times 2 times 3, that does equal 12. So your answer is 2 times 2 times 3, and we see that typed up right here. Here's another example. Here we have 30. So what is the prime factorization of 30? Well, 30 can break down in different ways. One way would be 3 times 10. So now with 3 times 10, 3 is prime. We can bring it down to the next line. 10 is composite. We can break that down further as a product of 2 times 5. Now 2 and 5 are prime. That cannot be taken further. So we have 3 times 2 times 5. But if you write this in order from least to greatest, we'd put the 2 first, and then the 3, and then the 5. So 2 times 3 times 5 is the prime factorization of the number 30. Here is one more example you can try. This is 45. So what is the prime factorization of 45? Well, we can break this down as a product of 5 times 9. 5 is prime. We can take that down to the next line. 9 is composite. We can break 9 down as a product of 3 times 3. So 45 is 5 times 3 times 3. But if you write it in order from least to greatest, we can put the 3's first and then the 5 at the end. So your prime factorization of 45 would be 3 times 3 times 5. So we've given you the process of prime factorization. We also gave you some practice with it. Now to finish off the lesson, we want to give you some tips on how to determine if a number can be divided by a particular number. All right, so for example, like if you're trying to figure out, can you break down 300? Can you divide that by 3? Or can you divide it by 6 or 2 or whatever, 5 or 10? There's methods we can use to figure out what can we break it down into. All right, and that's going to be our goal here on the next 2 slides. All right, so what I have here is going to be a table. All right, so don't get overwhelmed with all the information. We'll take this step by step. So what we have here in this far left column is the number that we're trying to determine if we can divide by. So we're trying to figure out ways to determine if we can divide by 2, if we can divide by 3, if we can divide by 5, 9, or 10. And then this column is the rule. So this is the method in which we can determine that. And then on the far column, we have examples of numbers that can be divided by the 2, 3, 5, 9, and 10. All right, so looking at this first row right here, how to determine if we can divide a number by 2. So the rule is, if the number ends in an even digit, so 0, 2, 4, 6, or 8, then the entire number can be divided by 2. So if you look at the first number of 22, notice the last digit is a 2. So that's an even number, so therefore we can divide 22 by 2. The next number is 318. Okay, 318 ends in an 8. That is an even number because it ends in an 8. What that means is that we can divide by 2. The third number is 5,786. The last digit is 6. That is an even number. So therefore, we can divide this entire number by 2. So that is the rule for dividing by 2. If it ends in an even number, we can divide by 2. Next one, we have 3. How to determine if we can divide by 3. So the rule is, if the sum of the integer's digits is divisible by 3, then the entire number we can divide by 3. So what does that mean? Well, if we take the number 81, for example, if we take those digits, 8 and 1, add them together, that's 9. Well, can we divide 9 by 3? Yeah, 9 divided by 3 is 3. So therefore, 81 can be divided by 3 also. All right, same thing here. We have 810. So 810, if we add up all the digits, 8 plus 1 plus 0, that would still equal 9, right? So because we can divide 9 by 3, 9 divided by 3 is 3, that means we can divide 810 by 3. So that is the step, or the process for that one. And we'll do one more example. Here we have 2,370. If we add up those digits, 2 plus 3 plus 7 plus 0, well, that gives you 5 plus 7, which is 12. And can you divide 12 by 3 without a remainder? Well, yeah, 12 divided by 3 is 4. So therefore, because you can divide the sum by 3, we can divide this entire number by 3. And that is the rule for dividing by 3. All right, now dividing by 5, that's the next one. To divide by 5, the number needs to end in a 0 or a 5. It's like 30 is our first example. That ends in 0, so we can divide by 5. 920 ends in a 0, so we can divide by 5. 8,655 ends in a 5, so we can divide by 5. So if it ends in a 0 or a 5, we can divide by 5. All right, and then to divide by the number 9. This is just like the divisibility rule for dividing by 3. All right, this one we have to add up the digits again, but here, if the sum is divisible by 9, then you can divide the entire number by 9. So here, example 1, we have 72. So if we add up those digits, 7 plus 2, that equals 9, right? Well, can we divide 9 by 9? Yeah, we can. 9 divided by 9 is 1. So because we can divide the sum by 9, we can divide the entire number of 72 by 9. Same thing with the next example. We have 657. If you add up the digits, 6 plus 5 plus 7, that gives you 11 plus 7, which is 18. Can we divide 18 by 9? Well, yeah, we can divide 18 by 9. That would give you 2. So therefore, we can divide the entire number by 9 without a remainder. So 657 is divisible by 9. In the third example here, we have 7,893. Again, if we add up the digits, 7 plus 8 plus 9 plus 3, that would give you 15 plus 9, which is 24. 24 plus 3 is 27. Can we divide 27 by 9? Well, yeah, 27 divided by 9 is 3. So because of that, we can divide the entire number by 9. So 7,893 is divisible by 9. So dividing by 9 and dividing by 3, to determine if that is possible, those two kind of are the same process. All right, you add the digits together and see if we can divide by 3 or by 9. Now, the last one is probably the simplest for most people. To determine if it is divisible by 10, okay, if it ends in a 0, we can divide by 10. So 80 ends in a 0, so we can divide by 10. 900 ends in 0, so we can divide by 10. 6,540 ends in 0, so we can divide by 10. So if it ends in a 0, we can divide the number by 10. So those are all the rules for divisibility. So those are just kind of tips to help you when you try to figure out the prime factorization of a bigger number specifically. Now the last slide will give you a little bit of practice with the divisibility rules. So here we have the number 945. So do the best you can to answer these before I give you the answer. So see if you can figure these ones out on your own. So the number 945, can you divide by 2? Or is it divisible by 2? Well, the answer is no. The reason is because the last digit needs to be an even number, and 5 is not even, so no, we cannot divide by 2. Now, is it divisible by 3? Well, to figure that one out, remember we have to add up the digits, 9 plus 4 plus 5. That gives you 13 plus 5, which is 18. Can we divide 18 by 3? Well, yeah, 18 divided by 3 is 6. So because you can divide that by 3, that means the entire number is also divisible by 3. Now what about 5? Is it divisible by 5? And the answer is yes, because the last digit must end in a 5 or a 0. It ends in 5, so therefore yes, it is divisible by 5. What about 9? Can you divide by 9? The answer to this one is yes. The reason is because if you add the digits together, as we did up here, we get 18. And if we can divide 18 by 9, then we can divide the entire number by 9. Well, 18 divided by 9 is 2. So we can divide by 9, which means we can divide the entire number by 9. Now, can we divide by 10? The answer is no, it is not divisible by 10, because the last digit does not end in a 0. So no, it is not divisible by 10. We'll give you one more example to practice with. So here we're being asked, is 690 divisible by, and we're going to ask if it's divisible by 2, 3, 5, 9, or 10. So is it divisible by 2? The answer is yes, because 690 ends in a 0. 0 is an even number, so because of that, we can divide by 2. Now, can we divide by 3? To determine that, we need to add up the digits, 6 plus 9 plus 0. That equals 15. And 15 we can divide by 3, which means 690 we can also divide by 3. So yes, it is divisible by 3. Now what about 5? Can you divide by 5? And the answer here is yes, because to divide by 5, the last digit must be 0 or 5. So it's a 0, so yes, it is divisible by 5. Now, is it divisible by 9? To determine that, we add up the digits, as we did already. We got our answer to be 15. And if we can divide this by 9 with no remainder, then we can divide the entire number by 9. So can you divide 15 by 9? Well, no, not without a remainder. So because of that, this would not be divisible by 9. Now can we divide by 10? And the answer is yes, we can, because the last digit is a 0, which is the rule for dividing by 10. So we had a little practice here with divisibility. Hopefully that was helpful for you. And that finishes our lesson for today, and we'll see you next time.